Welcome to Kitchen Table Electronics, Lesson 2, Part 2, More on Voltage Sources. In Part 1, we saw how to make a voltage divider, and we saw that when we tried to use the output of the voltage divider, we changed the voltage coming out of the voltage divider because of its high Thevenin equivalent resistance. A very useful concept we will use again and again. We also saw at the end of lesson 1 that even the Arduino power supply had a measurable Thevenin resistance. I hope you did the exercise and you will have ended up with a number around 20 ohms. So now we're going to investigate making continuously variable voltages and generating a good low Thevenin equivalent resistance power source from your continuously variable voltage. In order to generate a continuously variable voltage, we're going to use a device called a potentiometer. Here is the circuit schematic for a potentiometer. It consists of a resistor with a contact point here that can be slid up and down the resistor to form a variable voltage divider. So here is a potentiometer with the case removed. There's the shaft that moves the contact here. This outer contact here goes to a semicircular carbon track that goes all the way around to this other outer contact. The middle contact goes to this wiper here that has a little spring-loaded pressure pad that sits on this track at some point determined by this shaft. All right, let's see how the potentiometer functions as a variable resistor by connecting a meter between that middle tab on the potentiometer and one of the outer tabs. Here we have set the voltmeter to measure ohms, and you see that wiper somewhere in the middle of the track. It's a 10 kilo ohm potentiometer, and it's reading about 5 kilo ohms. And here we go, moving it towards one end, and we're increasing up towards 10 kilo ohms. We don't quite get there. And then we'll move down again towards the other end to go down to 0. Now, in order to use a potentiometer in our breadboard or with our Arduino, we're going to have to learn to solder wires onto our potentiometer. This is a skill you'll find very useful in the future, so please follow along and find out how to do this. If you bought the toolkit I suggested you buy in the introduction, you will have found a handy-dandy little soldering iron, complete with a soldering iron stand and some solder, and a sponge. You probably wondered what that was for. It's not for mopping your brow as you listen to these lectures. Wet it and put it on the soldering iron stand, and then let's take a look at soldering wires onto our potentiometer. Now, the first thing I want you to notice here is that I have cut these wires here to have quite a bit of free wire at these far ends. Recall this is because these wires like to break here where the insulation joins the bare wire, and you don't want them breaking off in your Arduino or breadboard without the ability to pull them out again. I've also hooked the wires through the tabs here. They're swinging loose, but they're mechanically connected, and I put this in a little vise so that I could hold it there while I solder. Okay, now I've got this wet sponge pad here. I've let my soldering iron heat up, and I am cleaning it. I'm actually steam cleaning it so that the end of the soldering iron bit gets nice and shiny. And then I am applying some solder to the bit so that it's covered in nice, fresh, shiny solder. Just a word here, your soldering iron comes with an on-off switch and a little temperature regulator on the body of the soldering iron. You don't need to turn it on until some minutes before you need to use it, and you don't want to leave it on because the bit will oxidize beyond repair if you do that. I also turned the temperature down a bit because I found this soldering iron pretty fierce. Okay, so we've steam cleaned the bit. We're tinning the bit right now so that it looks good and shiny. There we are. And now we're going to solder the connections. Now, an important point is you do not use the soldering iron to carry solder to the joint you're going to make. You place the soldering iron on the two components to be welded together, which is the wire and the tab, and you leave it there until the two metal components are hot enough to melt the solder onto the joint. And you do this by dabbing the solder down onto it. And when it's hot enough, it'll flow beautifully and freely and form a smooth connection, which when the solder solidifies, will then rigidly hold the wire onto the potentiometer, and you can see now they are rigidly connected. All right, now we've put some wires onto our potentiometer. Let's plug it into our breadboard and let's measure the voltage between the wiper and one of the connections on the side of the potentiometer. Here we're using our Arduino as the power supply. This red wire goes into the +5 volts and goes to one side of the potentiometer. This green wire goes to ground, and there are two ground connections here, and goes to the other side of the potentiometer, and the yellow wire is going to our meter. That's the yellow wire here, this is the ground wire, and this is going to the red lead of our meter. This fritzing circuit diagram doesn't look like our actual circuit because we have our wires on our potentiometer plugged into the board here. The fritzing circuit element is designed to print into boards, to plug into boards like this, so they look a bit different. But the wiring scheme is essentially correct. All right, we're going to switch our meter over to the volts range and look at what's coming out of the potentiometer. Okay, I see 4.8 volts. And as I turn the wiper of the potentiometer, I see this going down to 0 and then coming up again. Okay, so we have made a nice readout circuit using our digital voltmeter. Now, let's do what we really want to do in this class, which is to use digital means of reading out voltages. And our digital means are our Arduino microcontroller. So let's wire up a circuit to, instead of connecting this center pin here to the meter, we're going to connect it to this A0 pin. A0 through A5, remember, are the 6 analog inputs. These don't read voltage directly. What they do is take a voltage between 0 and whatever the nominal 5 volt supply is. As you know, that's about 5.9 volts, and turn them into a number between 0 for 0 volts in here and 1023 for 5.9 volts in here. And so if you are about halfway, you'd be reading around 512 on the output of the Arduino. So here's the circuit wired up with a breadboard. Once again, we're taking the plus and minus supplies from the 5 volts and ground. But now we have the wiper of the potentiometer connected across to A0. Don't forget to disconnect your Arduino while wiring it, just in case you make a mistake, and always check before you put the power back onto the Arduino. Now, the Arduino won't read the voltage unless it's told to do that. And remember, I promised you wouldn't have to learn C++ programming until the end of this class. And the reason for that is there are lots of pre-programmed examples that come in your Arduino IDE. So we booted up the IDE, I've gone File, Examples, Basics, and here to Analog Read Serial. And this comment section up at the top tells you that it reads an analog voltage from pin 0, analog pin 0 that we connected it to, and prints the result to the serial monitor. Now the serial monitor you'll find under Tools, you'll find a serial monitor which plots the numbers coming from the Arduino, or prints them rather, and lets you very usefully send instructions to the Arduino if you need to do that. It also has a tool called the serial plotter, and we'll use that in a minute. Anyway, bring up this sketch, and then if you're confident your Arduino is connected, just press this arrow here to compile and load it. If for some reason it doesn't load, go to the Tools, Get Board Info, and see if it's talking to the board. If not, set the COM port on Tools. We discussed these problems in the first lecture in this series. All right, let's take a look at what we get as we turn the serial monitor on with that program loaded onto the Arduino, and we're reading 1023 because the wiper is connected to 4.9 volts. But now we're turning the wiper down to 0, and you'll see the number dropping all the way down to 0. All right, so we'll close the serial monitor, and do close it. The serial plotter will not open if the serial monitor is also open. And we'll go back to the Tools menu on our Arduino IDE, and we'll open up the serial plotter, and let's see what we get. Now, the serial plotter is kind of annoying. It self-scales itself. So you see here it's going from 1017 to 1029 when the output is 1023. That's one reason we're going to use Python code to do our plotting later on, because of the limitations of this serial plotter. I've turned the knob down, I'm turning it back up, and whoopsie, the connections are pretty nasty. That, by the way, is why you will not actually, in modern electronics, use a potentiometer to control levels. You'll use something called a rotary encoder, but more of that later. Okay. So now I'm going to set the potentiometer to about halfway and just leave it so my hands don't shake things around, make sure the wires are connected, and turn on the serial monitor again after turning the serial plotter off. And you see with the wiper about halfway, I'm reading a number that's something like halfway between 1023 and 0. Now, let me take this circuit and let me put on the output going to the analog read pin 0 here, a load. Here I'm showing 1 kilo ohm, and let's see what happens when we now look at the serial monitor again. With the load, we've dropped from 253 to 151 as a reading. Of course, you expect this because you are loading the 5 kilo ohm bottom half of the potentiometer with 1 kilo ohm. But I'm going to let you practice your math now, and you tell me what the Thevenin equivalent circuit predicts, especially in terms of readings, given the way I've told you that the Arduino analog to digital converter works. So there's an exercise for you. Of course, you need to know the potentiometer had a resistance of about 10K, or about 5K in series with 5K when we had the wiper midway. How do you make a good voltage source that doesn't change all over the place when you plug in some arbitrary component? We're going to want to do this because we are going to use this voltage source as our way of exploring electronic components with the Arduino. Well, we use something called an operational amplifier, a miraculous chip. This is rather early in such a course to introduce the op-amp, but I do it shamelessly. Why? Well, I want you to learn that there is a chip for everything. Even if you were a hardened electrical engineer who understood operational amplifiers inside out, you'll encounter many situations in which you'll say, I don't know how to do that. And if you go searching on Google, you'll find somebody somewhere has made a chip to solve your problem, almost guaranteed. But let's go back to this operational amplifier. Here is the symbol for the op-amp, a little triangle like this. The apex of the triangle here is the output of the operational amplifier. And these two lines here go to a minus sign and a plus sign. These are the two inputs. This is called the inverting input. This is called the non-inverting input. And the output of the op-amp is proportional to the difference between the inverting and the non-inverting inputs. Now, a couple of other things you need to know about op-amps. The effective load presented by an op-amp to a source of voltage is really infinite. It draws essentially no current at all. If you get to design super sensitive circuits, you'll start to worry about that aspect of an op-amp, but certainly not in this class. Conversely, the output can drive some quite heavy currents, and the data sheet will tell you how much current and what the equivalent Thevenin resistance is of this output. Now, the second thing you need to know is that the gain of this circuit, differential gain, so for a voltage that's difference between these two pins, is essentially infinity, and we'll quantify that in just a minute. All right, now let's do what you always do with an operational amplifier, which is to apply feedback between the output and the input, here the inverting input. Now let's look at what happens. Supposing we set the non-inverting input here to 1 volt. And let's imagine that the output here goes a little bit above 1 volt. It's connected back to the the inverting input. And if we go above 1 volt, the inverting input sends the output down. So down it goes. Let's assume it goes down below 1 volt. Now, the non-inverting input is 1 volt. This point connected to the output is below 1 volt, but it's the inverting input. So now it's going to shoot up again to 1 volt. The only stable operating point is when this voltage equals this voltage, but get this, this here is a low Thevenin resistance source of current, and this essentially is an infinite resistor sampling the voltage on this input pin. So you've converted your voltage source from one that may have a terrible Thevenin equivalent resistance, Thevenin, to one that has a low Thevenin output resistance. Now, as I describe the operation of the op-amp, you might think, good heavens, that sounds like it's a recipe for instability, because it has to find this critical stable point. And you'd be absolutely right. That is one of the limitations of operational amplifiers. When I was young, they were very difficult to work with, but now they are made bomb-proof, and I'll talk a little bit more about that. However, the first problem you're going to encounter when you go searching the web for operational amplifiers is you will see connections to a plus and a minus voltage source. What's all that about? Well, usually one wants to operate this op-amp around 0 volts. So for example, with this pin connected to 0 volts and then feedback applied across here. And then that means that the inverting input would have to send this output down below 0 volts. And so you need a supply that is negative with respect to 0 volts. And so almost all op-amps require a dual power supply like this, and that's very complicated. We want to use our Arduino as our power supply, and guess what? There's a chip for everything. So if you go searching for a single supply op-amp, you'll find amongst others this, the TLV2462, and it's called a rail-to-rail op-amp. What that means is not only will it work from a single supply, so this is now grounded and this is up to V+, but by a miracle of electronic design, this point can swing from ground all the way up to 5 volts. And when we learn about transistors, you'll see that the engineers who designed this have done something quite miraculous. Now, suppose you really wanted to have an output that would swing negative. Well, guess what? There's a chip for everything. And this chip, the ICL7662, is one of several that take a plus 5 volt supply and generate a minus 5 volt supply. So if you really want to, and later on in the course we probably will, have both a plus and a minus 5 volt supply, you can do this with a chip that costs you $1 or so, as opposed to going out and buying an expensive power supply. Okay, here we are, data sheet time again. I offended you at the beginning of the course by talking about the ATO Mega microprocessor datasheet, which was truly intimidating. The datasheet for this op-amp is much less intimidating because it's much simpler. Let's take a look at the pinout diagram here. These chips all have a little fiducial mark, usually a little cutaway here or a little circle here or both. And this means when you look down on top of the chip with the pins pointing downwards and you see this little cutout symbol, the pin on the top left is always pin 1. And if you look at this, pin 1 is the output of operational amplifier 1. Pin 2 is the inverting input for operational amplifier 1. Pin 3 is the non-inverting input for amplifier 1. Pin 4 is ground, and pin 5, 6, 7, 8 is the plus voltage supply. And look at this. You got a second operational amplifier thrown in for free. Now, why did I choose this? Well, look. The single supply voltage supply can be 2.7 to 6 volts, perfect for our Arduino. I said this had a high input resistance. There are actually several parameters that control that. but let's just take one of them, differential input resistance. In other words, how many current flows between the plus and minus input pins. 10 to the power 9 ohms, a billion ohms. But look at the output impedance. Impedance, we're just going to use the word, let's say that says resistance. We'll talk about impedances later in this course. 33 ohms. And in fact, you'll see when you wire this thing together, it's better than that. Here are a few more things. I told you the gain was infinite. This is a plot taken from the data sheet of the open loop gain, so that's without feedback. Remember, when we wired the output to the input, the gain was 1 times. So here's the open loop gain of the chip with no feedback, plotted versus the logarithm of frequency. The gain is plotted also in log units. Decibels are 10 times the logarithm to the base 10 of some ratio. So in other words, if you had a gain of 10, the logarithm of 10 is 1, because 10 to the power 1 is 10. 10 times 1 is 10. The gain would be 10 dB. So let's go down here. Here is a gain of 10 dB, or 10 times. Now you'll notice that up to about 100 hertz, the gain is pretty constant at 90 decibels. So let's divide that by 10, that's 9. Let's raise 10 to the 9. That is a gain of 1 billion times. 1 billion times. So 1 billionth of a volt between the plus and minus input pin would result in an output voltage of 1 volt. I promise you, you'd have a very hard time testing that. Notice something interesting. The manufacturers of this chip have put components on the chip that roll this gain off as the expression for it. It falls on this log-log plot, as this straight line here. And they do this precisely for the reason that I mentioned on the previous slide, which is that if this whole point about finding a stable operating point sounds a little scary to you, it actually is. And at high frequencies where you can get unintended types of feedback, you want the gain to go all the way down to unity, and that's why the manufacturers roll the gain off like this. This doesn't matter very much if you're using the chip at unity gain or a gain of a few. So here's 20 decibels, which would be 10 squared, or a gain of 100. So you could do that without worrying too much. But you'll see that, in fact, as you increase the gain that you use, you'll want to limit the upper frequency that you use the chip at. This is characterized by something called the gain bandwidth product of 6.4 megahertz. And you'll see from this plot that 0 here, which is where unity gain in terms of decibels, and that's somewhere here between 1 and 10 megahertz, i.e. 6.4 megahertz. Okay, so that's the chip. We're doing unity gain. We're not too worried about frequency response. Life is easy for us. There are other things to look at on this data sheet if you make high gain amplifiers, input offset voltage, input offset current. We won't worry about that for now. So here is our circuit. Here's a picture of this chip. Here's the dimple, so that means this is pin 1 looking down on the top. And here again is that pin out I showed you. Here it is stuck into the board. Here's the ground from our Arduino coming around here and going to the ground on the chip here. Here's 5 volts from Arduino going around here and onto the 5 volt tab over here. We also have the potentiometer between 5 volts and ground. The wiper now is connected here, and if we go down here, we see that is the non-inverting input. The output and the inverting input are connected together by this little loop of wire here. And then we bring the output here to measure externally. And we're showing a 220 ohm resistor. I think I actually use a 1 kilo ohm resistor as a load. We're going to pull that in and out. Here's the schematic. So you can see here the potentiometer between the plus and minus 5 volt supply, the wiper going to the non-inverting input, the inverting input and the output connected together. And this is then the output. This is the ground pin, and this is the 5 volt pin. And here's a photograph of the bird's nest wiring that I made on my little board. Now, let's have a look at what that achieves for us. Here I show you what I'm reading as the output with the potentiometer wiper set about midway, and I'm reading about 2.345 volts with no load. Now I plug a 1 kilo ohm load into the position that I showed that 220 ohm resistor in the previous picture, and the output does drop. This is not a perfect voltage source, but it drops by only 5 millivolts. So, homework problem for you. What is the Thevenin equivalent resistance of the TLV2462? You'll find it's actually better than specified by that parameter that they called the output impedance. Right, we are ready to go in getting onto computer generation of variable voltages. To do that, though, we'll have to understand time varying voltages, and to understand those, we'll have to use our PC interfaced oscilloscope.